So we have one last page in the notes for Chapter 1, and this is an application example, and we're back to mixing tanks. This time we're going to be mixing we have a mixing tank that initially holds 300 gallons of water in which 50 pounds of salt has been dissolved. So initially is cueing us in that this must be our initial condition right here. So that's useful to keep in mind. Another brine solution is pumped into the tank. So there's an input that we're talking about here. So pumping into the tank at a rate of 3 gallons per minute. And then when the solution is well stirred, it's pumped out at a slower rate of 2 gallons per minute. So I'm going to highlight that, give it a different color. So this is going out at a rate of 2 gallons per minute. If the concentration of the solution entering is 2 pounds per gallon. Okay, so that's another piece of information for the input. First, determine the differential equation for the amount of salt in the tank present at any time, and then determine how much salt is present after 50 minutes. So the last little bit right there is saying, okay, so we want to know eventually, we want to be able to predict what is at 50 minutes of pumping. So we want to be able to come up with an answer after 50 minutes. But notice it also tells us to use the variable S for the amount of salt. Okay, so that's what we're going to do. So the first thing I like to do in situations like this is embarrass myself by trying to draw a picture. And so I'm going to try to draw a picture of what's going on with a mixing tank. And I'm just going to imagine my mixing tank kind of looks like a big marshmallow. When I was a little kid, I grew up not too far away from some large petroleum storage facilities, and they have these huge white tanks. And when I was a little kid, I always used to refer to them as the marshmallows because that's what they look like to me. So imagine we've got our water, our brine water in the mixing tank, and we've got an amount of water to begin with that's in there, right? Now we have an input that's kind of pouring in, dumping into the tank, and we also have some kind of output, right, to give us a sense of what's going on. Now this is a fairly simple situation where there's only one input and one output, but there's no reason why we couldn't have multiple inputs or maybe even multiple outputs. So drawing the picture helps kind of cue us in as to what's going on. Then off to the side, what we probably want to do is in words describe what we're talking about. So we're going to be talking about the rate of change of salt in the tank. And that's got to be determined by the inflow of salt into the tank minus the outflow of salt into the tank. Now keeping in mind, this is a rate of change, and so this is a rate, and so is this. And we know, because that's the way equations work, that all three of these have to have the same units. And since we're talking about a rate of change of salt, the amount of salt is going to be in pounds per, and it looks like minutes are the units of time that we're dealing with here. And so each one of these terms has to be in pounds per minute. So just setting things up, making sure I understand what's going on. Last little bit, I like to kind of mix and match here. And I've got an inflow rate. My inflow rate is the green information up there. And my outflow rate, that was the orange. So the terms that make up the term that makes up the inflow is going to be the information from green, and the outflow is going to be the information that I underlined in orange. So let's write this as a differential equation, and the next step is to kind of use variables and such, and numbers. So this is going to be ds dt on the left side. The right side is now going to be my inflow rate, which is 3 gallons per minute times 2 pounds per gallon, and those two multiplied together, gallons per minute times 2 pounds per gallon If I do this right, then the gallons and gallons cancel and I get pounds per minute, and that's the way I want it. So that one's not too bad. That one's pretty easy. Just two numbers multiplied together. So this is going to be 6, just the number 6. But the outflow is a little bit more complicated because what's coming out is definitely coming out at 2 gallons per minute. But what I need now is some concentration of how many pounds of salt is there per gallon. Well, what's coming out of the tank is the amount of salt divided by the number of gallons in the tank. Now, the amount of salt in the tank at any time, that's just S. So that's S of T, and that'd be in pounds. But the number of gallons in the tank, well, it initially starts off with 300, right? 300 gallons. But it looks like my inflow and outflow rates are definitely not the same. So the bottom is going to be 300 gallons plus the difference between these two. It looks like it's gaining at 1 gallon every minute plus 1 gallon per minute times how many minutes have gone by. Now you'll notice this is gallons, and this is gallons per minute times minutes. And so the end result is the bottom is going to be in gallons. The top is pounds. The gallons up here and the gallons down there cancel out, leaving me with pounds per minute. Now this is a fairly complicated denominator. That's unlike something that we've seen before. Usually it was just a fixed amount because the inflow and the outflow were the same. But that's not how it is now. So moving ahead, we need to figure out what to do. Well, we're going to drop the units since we know they behave properly. And let's write our differential equation. ds dt equals 6 minus, 2 times s over 300 plus t. So 2s over 300 plus t. And now we have our differential equation. And we also have something that is a little bit more complicated than what we've seen before. So what do? Well, we can use the integrating factor method. Why, of course we can. And if we use the integrating factor method, we're going to move everything that has an s in it to the other side. So we'd have ds dt plus 2 over 300 plus t, notice what I did, times s. I leave everything but the s sitting out in front. I factor it out front. And so this thing in here, this thing up front, is going to be my g function. And that's what I can use to figure out what my integrating factor is, what I need to multiply through. So I say my g, in this case it's g of t, is equal to 2 over 300 plus t. And that means my integrating factor, mu of t, is what I get when I take e to the integral of g of t dt. What is the integral of this thing? Ugh, it's a little ugly. The 2 comes out front, and we just have 2 times the natural log of that denominator. So this thing becomes e to the 2 natural log of 300 plus t. Again, I can't use the e natural log trick and have them cancel because there's a 2 sitting in front. So I'm going to pull that 2 inside, and this thing becomes quantity 300 plus t squared. That's my integrating factor. That's what I have to multiply both sides of this equation by. Right? Oh, whoops! I forgot to write I forgot to write the other side of the equation. All this is equal to 6. The 6 is still there. So when I multiply both sides of my equation by my integrating factor, 300 plus t quantity squared times ds dt plus 2 over 300 plus t times s equals 6. That's my whole equation right there. I wind up with, on this side, if I did it right, I should have the integrating factor times s. And that will be the derivative of that, should be the left-hand side. And so I get d dt on the left-hand side of integrating factor times dependent variable, the derivative of that, and on the right-hand side, 6 times the integrating factor. Now I got to integrate both sides. This side's pretty easy. It's just 300 plus t quantity squared times s. The right-hand side is just the integral of this thing, right? Which, with a little bit of u substitution, I think you can probably see that it turns out to be just 2 times 300 plus t quantity to the third power plus a constant. I kind of skip the step where I'm integrating. I do it in my head. But if you need to write it out, you need to write it out. It's not the end of the world. Now, you'll notice over here, if I can divide both sides by that 300 plus t quantity squared, then I'll get s of t equals, I'll have my general solution. Dividing this term by the quantity squared just gives me 2 times 300 plus t plus my constant's got to get some love, so it's c over the quantity 300 plus t squared. And that's my general solution. So I can use my initial condition, which, if you remember, way at the top, my initial condition was it initially holds 300 gallons, but there's 50 pounds of salt. That's my initial condition. That is telling me that in this case, S of 0 equals 50 pounds of salt. So down at the bottom, I'll use my initial condition. S of 0 equals 50 to find the particular constant C. Now, plugging in 0 for t means this just becomes 600. The bottom here is just 300 squared. And so it's going to be 50 minus 600 times 300 squared. So it's going to be kind of an ugly looking number. C turns out to be just negative 550 times 300 squared, right? Now, I don't know what that is off the top of my head, but I've got a computer that's going to do that for me. And then, of course, the last step in this process, once I've got my C, then I know my particular solution. And then my very last step is it's asking me to make a prediction. So use the particular solution to find what is S of 50. Now you might say, well, wait a minute, 50 minutes goes by. That means there's going to be another 50 gallons, I should say up here, another 50 gallons in the tank. So is this tank big enough? Well, it doesn't really say, but it does assume that this is a very large mixing tank. So I think we can presume that it can hold another 50 gallons. But let's see what happens when we do this. And I'm going to do this in Maple. So I'm going to hop over to Maple and say, hey, Maple, I think you can help me with this. I'm going to have Maple de-solve this problem all in one go, which means I have to put it in the brackets. And so I'm just going to type in my differential equation. So this is going to be S of t, well, I'll use capital S, I guess, ds dt equals, on the other side it was 6 minus 2 times S of t divided by 300 plus t. So that's my differential equation, and then my initial condition was S of 0 equals 50. So let's see what Maple says is the particular solution. And it should give me an exact value for what the value of the constant was. So I'll write that down on my paper. But it looks like 600 plus 2t minus this big number over 300 plus t quantity squared. And that looks exactly like the equation that we came up with. But now, fortunately, I can say to Maple, hey, would you evaluate the right-hand side of, I don't think I'd need to do caps. I think I just do right-hand side lowercase. Evaluate the right-hand side of, then I'm going to say, let me scoot this up so you can see a little bit, the line, the identifier here, number 4. So evaluate the right-hand side of 4 when t equals 50. Now if I just type in 50, it's going to give me an exact answer. Let me show you. And that's great and all, but I want to be able to say it as a, a number that humans would understand. So I'm going to go back up here and say, nah, not 50. Give me, in terms of 50.0, give me a decimal. And Maple says, oh, okay, you want me to approximate. So 295.92, call it. And so if I go back to my work here on the paper, 295.92 is what this is approximately equal to. But 295.92 what? What did we find? We found S, which is in pounds of salt. And if you just give the numbers, the units are important. They matter. That's my approximate answer, but it's pretty good. You're out to the 100th of a pound, which is pretty good. Now, there are some other things that you might want to think about. I'll add a little bit more to the Maple document so you can kind of see how we might play around with this, including making a DE plot of this to kind of visualize what's happening to the solution curve over time. So be sure to check out the Maple document for this. But that gets us through the end of Chapter 1. We were able to use our integrating factor method. But you know what? We could have done this with the lucky guess method. It just would have been a lot uglier. So, hopefully that's enough for you to chew on for right now. You've got plenty to work on, plenty to keep you going. Make sure you get going on that homework. And I'll see you later.